Last class I discussed about the no load phasor diagram of transformer and equating the equation, that is E1 primary winding EMF is root 2 pi F phi max N1 and E2 equal to root 2 pi F phi max N2. Now today we already known about that what is ideal transformer. The ideal transformer, that is the winding resistance is negligible. Primary winding resistance suppose R1, secondary winding resistance suppose R2, that is the winding resistance is very negligible. All the flux set up by the primary must link with the secondary winding. That means there is no leakage flux in case of ideal transformer. And another, the core loss, that is hysteresis loss and eddy current loss, we are already known about that. That is negligible. Okay, and core has constant permeability, that is the magnetization curve is linear. Remember that in case of ideal transformer, that the magnetization curve is linear. So these are the four characteristics of ideal transformer. First, you look at the picture I draw here. In primary side, number of turn N1 and connecting a source, alternative source V1, and here in secondary number of turn is N2, and with the help of switch S we are connecting a load. Suppose the load have impedance ZL. Okay, if the switch S is closed, that is ZL are now connected in secondary. Since the secondary resistance is 0, that is we are actually working in ideal transformer. Suppose this one is the ideal transformer. If the secondary winding resistance is 0, then the induced voltage in secondary, that is E2, equal to the voltage across the load, that is V2. Okay, now according to the Lenge's law, we are known about the Lenge's law, that is effect always oppose the causes. Now according to the Lenge's law, the secondary winding current I2 is flow in such a way that the secondary MMF I2N2 always oppose the mutual flux phi. Remember that according to the Lenge's law, the I2 flow in such a way that the MMF produced in secondary, that is I2N2, always oppose the mutual flux phi, so that the current leaves from M terminal and enter to the G terminal. So here I2 current leaves from the M and goes to the G terminal. Okay, so that's why the M terminal is positive and G terminal is negative. It is very clear. I2 current flow from M terminal and it enter the G terminal, so that the M terminal is positive and G terminal is negative at now. Now if you look at the primary side, that is the current direction A to B. So we can conclude that when primary terminal B is positive with respect to C, then the secondary terminal M is positive with respect to G. Okay, again we say that the F2 is actually oppose the mutual flux phi. So that F2 reduce the flux phi. So any reduction of flux, that means it will reduce V1. As we know, in case of ideal transformer, that is V1 equal to minus E1. Okay, again any reduction of flux would reduce the E1. Okay, we know that the E1 equals to root 2 pi f phi max N1. So reduction of flux means reduction of induced EMF E1. Again we know that the E1 is equal to the V1. Okay, the applied voltage, if the applied voltage is constant, then E1 should be constant. If the applied voltage, V1 constant, then U1 should be constant. Okay, so for that reason it will draw a primary current, that is suppose I1 dash, from the source to neutralize the demagnetizing effect of I2N2 or I2. Actually F2 is reducing the phi, that is opposing, reducing the phi, so that its effect is demagnetizing effect. As we know, V1 is constant, so that in case of ideal transformer U1 is constant. Okay, now constant in the flux, the source must draw a more amount of current to neutralize the demagnetizing effect of I2, that is I2N2 effect, that is F2. Okay, so while load is connected, primary draw a current, suppose I1 dash. Okay, so primary winding draw more current, suppose I1 dash, from the source to neutralize the demagnetize effect of F2, that is I2 into N2. Very simple. So compensating MMF, that is I1 dash N1 in primary is equal to the secondary MMF, that is I2 into into. Okay. So I1 is the I1 dash is the that is the load component current when we are connecting the load in secondary side. That is the load component current in primary when we connecting the load in the secondary. Okay, so this should be equal to I1 plus IE, that is the no load exciting current. If the exciting current is neglected, if exciting current neglected, then I1 dash equal to I1. So very simply say that the primary MMF in transformer, primary MMF is equals to the secondary MMF in transformer. That is I1 N1 equal to I2 N2. So we are already known that in previous class, that is V1 by V2 equal to E1 by E2 equal to N1 by N2. Now from this equation we can write that is I2 by I1. Remember that equation, that is V1 by V2 equal to E1 by E2 equal to N1 by N2 equal to I2 by I1. From this equation we can write that the V1 I1 equal to V2 into I2, that is primary volt ampere is equal to the secondary volt ampere. Now suppose we are taking that the primary side power factor cos of theta 1, that is primary side PF is cos of theta 1. Okay. Now as we know, the in case of transformer, when we draw the phasor diagram, that is the flux is taken as a reference, so phi taking as a reference, this is the phi. Now as for the equation, that is Vt V2 equal to E2 E1. Suppose this is the ideal transformer, in case of ideal transformer, so V1 must be equal to E1, so V1 is minus of E1. Okay, now this is your exciting current IE. Okay, IE, and this is the load component current due to the load I1 dash, so that the total primary side current is I1. Okay, now this is the power factor angle, as we says that the power factor cos of theta 1, that is the theta 1 angle. Okay, now primary MMF is equal to the secondary MMF, so this is your primary MMF, that is F1, and diametrically opposite, that is the secondary MMF F2. Okay, I2 is in phase with F2, so this is I2. Okay, so this is the phasor diagram of ideal transformer.